Välkomna till Kungliga Vetenskapsakademin och den här presskonferensen då vi ska presentera årets Nobelpris i fysik. Welcome to the Royal Swedish Academy of Sciences and this press conference where we will present this year's Nobel Prize in Physics. We will keep to our tradition and start in Swedish and then continue the presentation in English. And you are of course welcome to ask questions later on in either language. Jag heter Hans Ellegren och är ständig sekreterare här på Kungliga Vetenskapsakademin. På min ena sida sitter professor Olle Eriksson, ordförande för Nobelkommittén i fysik. Och på andra sidan professor Göran Johansson, ledamot av Nobelkommittén för fysik och sakkunnig inom ämnet. My name is Hans Ellegren. I'm Secretary General of the Royal Swedish Academy of Sciences. To my right is Professor Olle Eriksson, Chair of the Nobel Committee for Physics. And to my left, Professor Göran Johansson, member of the Nobel Committee for Physics and one of the experts in this field. Årets pris handlar om att möta kvantmekaniken på ny skala. This year's prize is about encountering quantum mechanics on a new scale. Kungliga Vetenskapsakademin har idag beslutat att utdela 2025 års Nobelpris i fysik till John Clark, University of California at Berkeley, USA, Michel Devoré, Yale University och University of California at Santa Barbara, USA, och John Martinis, University of California, Santa Barbara, USA, för upptäckten av makroskopisk kvantmekanisk tunnling och energikvantisering i en elektrisk krets. The Royal Swedish Academy of Sciences has today decided to award the 2025 Nobel Prize in Physics to John Clark, University of California at Berkeley, USA, Michel Devoré, Yale University and University of California at Santa Barbara, USA, and John Martinis, University of California at Santa Barbara, USA, for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. Professor Eriksson will now give us a short summary of the prize. Please.
This year we celebrate the centennial anniversary of the discovery of quantum mechanics and the seminal publication of Werner von Heisenberg. This is a theory of the microcosmos, that of atoms and electrons, and there is no advanced technology used today that does not rely on quantum mechanics and quantum physics. Examples are easy to find in the room: mobile phones, computers, cameras, and the fiber optic cables that connect our world. Quantum mechanics stands on several pillars, most prominently the energy quantization and the quantum mechanical tunneling phenomenon. This year's Nobel laureates have shown experimentally in studies published in the mid-1980s that quantum mechanical effects are found in new vistas outside of the realm of the microcosmos, hence embracing macroscopic objects.
Thank you, Olle. And Professor Johansson, can you give us a more in-depth presentation of this year's prize?
Yes, thank you. So, this year's prize is about quantum mechanical tunneling. This is a quantum mechanical effect that was discovered soon after Erwin Schrödinger published his famous wave equation in 1926, almost exactly 100 years ago. Soon after it was published, solutions were discovered where a particle could penetrate a classically impenetrable barrier. So to the left here, you see that exemplified by a wall, and the little boy throwing a classical ball onto the wall. It always bounces back. However, quantum mechanical particles can sometimes appear on the other side of this classically impenetrable wall, and it is as if it dug a small tunnel through the barrier. Hence the name. Soon after tunneling was discovered, it was also discovered that it's not only an astonishing theoretical prediction, it also has practical implications in the subatomic world. So to the left, you see a big nuclei, lots of protons and neutrons, and so-called alpha decay of this nuclei can be explained by the fact that the alpha particle, 2 neutrons and 2 protons, is bound, it's part and bound to the nucleus by a barrier. And classically, it would never ever leave the nucleus. However, due to quantum mechanical tunneling, it can appear outside of the nucleus, and thus you have radioactive decay. And the fact that it's quantum mechanical tells that it's a completely random process. And also by calculating the width and the height of the barrier, you can calculate the average waiting time for this decay or the half-life. So, we understand that quantum mechanical tunneling is important in the subatomic world. However, can we observe larger systems that tunnel? This was a question raised by Nobel Laureate Anthony Leggett in 1978.